Hi, my name is McPherson, and I'm going to talk to you today about fractals, complexity science, and the visual arts. The overarching goal of this project is to bridge the gap between humanities, arts, and social sciences by creating a unique and quantitative method to apply physics and math to the study of art. Current research in this area includes a research paper on Jackson Pollock paintings that uses fractional dimensions and neural network analysis that looks at the content of different images. Relaying emotion in visual arts can be analogous to relaying entropy or information in general, which is quantified by using means of entropy. The goals of this project are to combine statistical physics with mathematics to differentiate between different ambiances in different paintings and to understand factors that contribute to ambiance using entropy. One of the main areas of background and motivation for this project is art theory. Some of the basic components that make up any painting are color, light, line, texture, and composition. Current element analysis techniques lack ways to sort of incorporate the influence of these components into their studies. So by using entropy, we can study art theory a little bit more directly. Next, an area is complexity science, which just uses entropy to quantify a variety of different kinds of informations. And before we can begin, we have to figure out what exactly we mean by ambiance. So studies have shown that the human brain is capable of understanding fundamental emotions, including awe, contentment, disgust, calmness, happiness, fear, and sadness. So these emotions make up the basis of this study, and ambiance is actually defined as the conveyed emotions of a painting. The two images in the bottom left of the poster show the baseline images that were used to make and perfect the methodology of this project. Figure 1 is a Claude Monet painting titled The Bridge Over a Pond of Water Lilies, and Figure 2 is a randomly generated black and white pixel grid. Before any of the paintings were studied, they were all put through an image processing scheme. The first step is to scale and resize them. All paintings were scaled down from their original size to be a 100 by 100 pixel using bilinear interpolation, which is a way to preserve the content and relative positions of similar groups of pixels within the picture. The next step is to threshold the images. They all come in as color, and then they are converted to grayscale and then to black and white. So the thresholding value is picked as a middle between 0 and 255, which is the range of white to black pixels. And then anything above or below this threshold becomes black or white. The four images in the second column show various different example thresholding values. For this study, a threshold value of 150 was chosen to be the middle because it preserves the content of the image the best without straying too far away from the true middle of black and white, which is 128. Whenever these images are processed, the scaling, resizing, and thresholding actually changes the microstates since they are defined as the number of black and white pixels. So the changes in singular value decomposition and the changes in entropy that are just induced by the image processing are the basis of error within this investigation. 4 Monet paintings were studied. These are Figure 1, Figure 3, Figure 4, and Figure 5. These were chosen because 3 of them have similar ambiances as calm, contentment, and happiness, and the third one is sadness. So this way, it could be seen if the methods could distinguish between happy and sad, but also to see how good they were at distinguishing between similar ambiances. The first step of studying these paintings was to put them through singular value decomposition, which is a way to get generalized eigenvalues from non-traditional matrices. These diagonal matrices were then used in the generalized Rényi entropy calculations as shown in equation 1. The first order Rényi entropy, or sometimes known as the Boltzmann or von Neumann entropy, was used with a Q equals 1 and is shown in equation 2 in a modified formats where rho is the diagonalized matrix obtained from doing SVD. If you look further down the third column of the poster, there is a graph showing the SVD decompositions of each of the 4 paintings where sad is in red. And you can actually see there is a little bit of a difference visually between the sad painting SVD and the other 3 similar ambiances. And this difference is actually preserved throughout the first order and second order Rényi calculations shown in tables 1 and in table 2. The second order Rényi entropy is particularly interesting because it has implications within quantum chaos. It is used as a diversity measure in social sciences, and it is related to the inverse participation ratio. And if we qualitatively look at these paintings, it actually makes sense that the 3 sort of happier paintings have a higher Rényi entropy and a higher diversity because there is more difference in kind of the color, the shapes, and the different compositional elements than there is in Figure 5 in the Satyr painting. This case study supports the conclusion that there is actually a measurable difference between ambiances in works of art, particularly between happier and sadder paintings. One of the biggest areas to improve on in the study is to include more Monet paintings and to move past Monet so that we can get a better variety of different ambiances and different art styles. These conclusions also suggest the possibility that the eye can actually see entropy and complexity and uses this information to interpret and conclude the ambiance of a painting. Other next steps include expanding the relationship between entropy and diversity and entropy and fractional dimensions, and exploring the interpretation of color, since this is one of the most important parts of art theory within the defined microstates of this project. Thank you very much for listening.